Today I will be presenting a brief tutorial on battery management systems. So the flow for the today's presentation will be like this. So first we will be introducing the lithium ion batteries, and then what is a BMS, what is the battery management system that we will be talking about. Then several functionalities of BMS like measurements, monitoring, evaluation, and then we will look at one of the evaluation that is important for a lithium ion battery, that is state of charge estimation, SOC estimation, that we will look at, and we will look at one example of a particular algorithm that we can implement readily through any script. So how we can do that, that we will see, and then some of the BMS topologies and some advanced algorithms for management of batteries like cell balancing and all. So that will be the flow of my presentation today. So starting with lithium ion batteries. So before going to batteries, we should know how the battery is constituted of. So first it is a cell. So the cell voltage varies between, let us say, 3 to 4 volts. So that is the typical lithium ion cell rating, and if we combine them in a parallel combination, so we get a block. So in parallel combination, the voltage stays 3 to 4 volts, but the ampere hour rating, that is the current that can be pumped into the cell or that block, increases. So now we have a cell and a block. So we can use either of them to make a series connection. So if we connect several cells in series, then we get that cell current rating, but we get a battery of 12 volt rating. Let us say nominal of 12 volt. Based on the chemistry, if the voltage of the cell changes, then accordingly that battery voltage will also vary. So if we use, let us say, blocks, then the current rating will be that of the block and the voltage rating will be 12 volts, the number of series cells. Now the 12 volt battery as it is, we can use it, but for particular applications such as traction, for satellite power supplies, depending upon the exact requirement, we will do a series parallel combination, and which creates a battery pack. So that is what is present inside the electric vehicles. Let us say a car, we see a huge battery pack on the floor. So that is nothing, just a series parallel combination of such 12 volt batteries. So this pack voltage, I have not represented any voltage or current, because this can vary depending upon the number of cells or number of batteries that you are connecting in series and parallel. Accordingly, the pack voltage and current rating can vary. So these are some representative pictures, like this is a cylindrical cell, and this is a pouch type of 12 volt battery. So this batteries that we find inside our mobile phones, they are the pouch. So those are pouches, and that's why when we open it, when they are damaged, it gets swollen. So it is a pouch type of battery, and this is a figure of different 12 volt batteries connected in series. So this constitutes a battery pack. So nominally, if we have 12 volt batteries, if we connect 4, then we have 48 volt pack, 60 volt pack, 72 volt pack, like that. So why lithium ion batteries? Because they have the highest energy and power densities as per the studies, and they are available in different types of formats that we just saw, like cylindrical or small and large cylindrical, prismatic pouch, like we see this zinc carbon batteries, 9 volt batteries, that is prismatic power structure. Then we have pouch, and we have what is lithium ion? Lithium ion chemistry is a lithium based chemistry. So lithium will be at one terminal, that is anode, and then based on the cathode composition, the chemistries will vary. So here we have lithium cobalt, lithium manganese, nickel cobalt, lithium iron phosphate, lithium manganese, titanium, like that. We have different battery chemistries. Based on the battery chemistry, the nominal voltage, that is this 3 to 4 volt, or even beyond that, it can vary. The power density as well as the energy, everything can vary based on these chemistries. So for traction purposes, based on literature, lithium phosphate and lithium titanate based battery packs are widely used because of their safety and their energy density. So these, according to references, these are the widely used chemistries for traction purpose. So coming to why BMS. So first we should know why we are using a BMS. So whenever we are using any cell or battery, so we have to ensure the safety of its operation. So for any battery or cell, a safe operating area is defined. That safe operating area is bound by the current, temperature and voltage. So we have to operate it within a particular range of currents, temperatures and voltages. If we do not do that, if we don't operate it in the safe operating area, then let us say we may end up overcharging the cell, we may discharge it further, we can increase the temperature inside that cell or the battery pack, which can eventually lead to thermal runaways. So that's why when we have seen like in past like several batteries inside the vehicles, they have caught fire. That is most of the reason behind that is thermal runaways. Then charging and discharging at higher currents. We all talk about fast charging, but how safe is that? Or are we degrading the battery? Is the battery life still 10 years, 15 years, or is it gone down by 3-4 years? So those things we need to see. Like if it is operating at the safe operating area even after fast charging, then it is fine. If it is not, then it's a problem. So these things we should keep in mind when we are talking about lithium-ion cells or batteries. Now coming to the safe operating area, so for this cell, like lithium iron phosphate 26650 energy cell, so the charging current for one cell is specified as 1.6 amperes, and the voltage during the charging process can vary from 2.75 to 3.65 volts, and we can charge it in this temperature range 0 to 40 degrees Celsius. So this shows the safe operating area of this cell while charging. So if it goes out, then we have to stop the charging or we have to stop its operation. Similarly, while discharging, it can discharge maximum of 3.2 amperes, and then it can the voltage, the terminal voltage can vary from 3.4 volts to 2.5 volts, and while discharging the temperature range is a little bit wider, that is -20 to 60 degrees Celsius. So again, so these plots show the safe operating area of this lithium iron phosphate cell. Now what is, so we were talking about why BMS. So BMS is there to ensure that our battery or the cell is being operated in the safe operating area. So goal is to ensure the safety, and how it is accomplished. So BMS in itself, after it detects the condition, abnormal condition, it can send a signal to the charger, or it can in itself stop the charging. So there are two ways a BMS can act once it detects an abnormality. It can send a signal through any communication protocol to the charger that stop charging, the battery is in danger. It can stop the charging, or it can itself act and open a contactor or a relay so that it can disconnect itself from the charger. So these are two ways in which the BMS can protect the battery once it detects any abnormality. So yeah, that's what we just discussed. BMS stops the charging or requests the charging to be stopped. So coming to the BMS functionalities, so this block shows a overall representation of a battery management system that can be employed for any cell, battery or a pack. So here we have the external system, and here we have let us say the battery. So first we have the measurements, then the measurements can be used to do management. We will go in detail into each of them. Then the measurements can be used to perform some analysis or evaluations. Then those can be used to store in a cloud-based storage or any app, so that we can monitor the life of the battery or the operation of the battery, its parameters over a large period of time, because these are meant to last for, let us say, 5 years. So we have to get the data. And then communication. So the BMS in itself cannot do anything. It has to communicate with a system, let us say a simple charger even. It has to communicate with the charger so that it gets appropriate currents, voltages, charging profiles, like that. So starting with the measurement. So what are the basic measurements that we need to perform? That are basically cell voltage, battery or the cell temperature, and the battery current. Right. So we will go into each one of them. So measurement of cell voltage. Why it is essential? Because we have to maintain it within a particular band of voltage. We should not perform overcharging, or we should not charge it below a certain voltage. Also, the voltage of each cell can differ from each other. There can be imbalances in the cell voltages, and why it is essential and how will we tackle that, that we will be discussing in the battery balancing or the cell balancing part. Then why one more purpose why voltage measurement is important is because we can use the voltages to determine the state of charge. So there are different algorithms for estimating the state of charge. One of them is by looking at the terminal voltages or the open circuit voltage. So for that, voltage measurement needs to be done. And so this is one representative picture of like here we have 5 cells. So we have 5 sensors which are sensing the voltages, then they are feeding it to a analog to digital converter or ADC, and that is feeding every data in digital domain to the microcontroller unit. So so most of the platforms that we use today for computation are digital, like DSP based or FPGA based. That's why we need the A to D converters. Now, while we use these A to D converters, we have to be careful because the voltage sensing requires better accuracy and sampling rate. So accuracy we will be discussing in the next slide. Why sampling rate is important? Because let us say the cell is completely undercharged. Then if we start pumping in current, then the voltage can vary suddenly. For that, we have to sample it at very small time steps so that we get the accurate characteristics. If it is in the plateau region where the voltage is more or less flat, we don't need that high sampling rate. That's why the sampling rate matters. So, and how do we use it to perform computations of SOC or the health or the battery? So that will be impacted by the sampling rate. Then coming to the like isolation. So some of these batteries are like high voltage batteries. Like in battery packs, they can go up to like 400 volts, 800 volts. So they need to be isolated from the low voltage systems. So there is no shock hazard and all. So that's why isolation may or may not be required. So based on the application, it has to be taken care of. So now coming to the accuracy. So this is a plot of the open circuit voltage of a cell of the lithium iron phosphate cell with its SOC. So open circuit voltage means when there is no current. So the current is 0 because there is battery internal resistance. So when we pump in any current or take out any current, then the terminal voltage can vary. That is different from the open circuit voltage. So battery SOC has a relationship with the OCV, and this is highly non-linear. So let us say we want to determine if our battery is fully charged or fully discharged. Then we can look at these ranges. If our battery voltage is in the vicinity of 3.5, 3.55, 3.65 like that, then we can determine that okay, the cell is fully charged. This is the example for a cell. So if we are connecting multiple cells in series, then appropriately we can scale up the calculations. So similarly for here, at fully discharged, the voltage is lower, like 2.5 volts, so 2.4 volt, 2.5 volt like that. So to detect fully charged or discharged conditions, like I want to be at the extremes, I don't want to predict any SOC, then 100 millivolt of accuracy is still fine for me. I can get away with it. But let us say I want to perform SOC estimation at either end of the curve. So here we can see that it is changing. So here I have 3 regions. So this is near to fully charged, this is fully discharged, and this is the plateau region. So let us say here we are in this zone fully discharged, then the battery voltage changes with SOC. It is a fairly good change. So that's why let us say 10 millivolt accuracy is fine. But in the plateau region, the voltage varies very slowly or the change is quite small. So that's why in order to detect that, we cannot use the same accuracy. We have to go for even higher accuracy. That's why in order to estimate the SOC in the plateau region, we need 1 millivolt accuracy. Similarly, to perform cell balancing while charging, 50 millivolt of accuracy. So these are collected from a reference for this lithium iron phosphate cell. For different chemistry, these voltages can vary. These voltages can vary. So let us say I have a full scale ADC of like a 5 volt. So if I want to get 100 millivolt accuracy, I have to use a 6 bits. And if I have to do 20 millivolt accuracy, I have to use 8 bits. So this calculation is fairly simple. Like let us say we have 6 bits, and then how much we can measure on a full scale of 5 volts. So 5 divided by 2 to the power 6, rounded up to its higher like decimal or a whole number. So that gives 100 millivolts. Similarly, if we want to get 1 millivolt accuracy, then we have to use 12 bit ADC. But with the higher the resolution goes, the cost of the ADC also goes. And if you have to monitor the voltage of each cell and you have hundreds of cells connected in series, then you have to put hundreds of such ADCs, and those ADCs also then they have to send that to the microcontroller, and we have to perform the computations for each one of them. Let us say we don't want to spend that much on the ADCs. So what we can do is we can put selectors and we can mux them. So let us say we have certain cells. Let us say I have 5 cells. So previously I showed the representative figure where I am measuring the voltages of each cell. So I have sensor everywhere. So I am using 5 sensors and 5 analog to digital converters. But then what I can do is I can put a mux, I can select that which voltage I want to send. So let us say again I have 5 cells, but now I have a selector here. So now I have a selector and it has 5 terminals or 10 terminals if you want to measure differential voltage, and here it will send out only one signal. So we can select, like okay, in the first time, let us say we are computing digitally at a time step of Ts, then in the first Ts you send me this cell voltage, in the second Ts you send me this cell voltage. So it will be done serially. But if we put separate sensors, separate ADCs, then we can send all those information parallelly to the microcontroller. The control can be fast, but here the control again computation speed will be limited. So this is just an example of how the voltages of the battery or the cell can be monitored or measured to perform these computations. So then coming to cell temperature, why it is essential? Again, we have to maintain it in the safe operating area, and we have to warn the system to stop the operation, charging or discharging in case of any abnormal temperatures. Plus there are systems which can perform active cooling of the batteries or the cells. They can engage or disengage a particular type of cooling mechanism. They can turn on a fan, or maybe they can open a valve and there will be a heat sink through which liquid flows. So something. So cooling mechanisms can be activated by sensing the temperature. So how it is done? We can measure the temperatures by using thermistor, which are like resistors. So its resistance changes with temperature. And then there are NTC and PTC, negative thermal coefficient, positive thermal coefficient. One temperature rises, one temperature falls. Means resistance rises, resistance falls with temperature. Then we have thermocouples, which is a temperature to voltage transducer. So based on the temperature, it will generate a proportional voltage, which is being fed to the ADC or our microcontroller. So these are the pictures of this is a NTC and this is a typical thermocouple. So these thermocouples we can use it with our multimeters as well, which have a conversion from temperature to voltage. Then coming to the current measurements, so we have to maintain the currents while charging, discharging. We should not charge it at a higher rate, that can lead to anodization and then dendrite formation, something. There are a lot of adverse effect of charging the batteries at higher rates or discharging the battery at higher rates. Then like we saw, voltage can be used to measure the SOC or compute the SOC. Similarly, the current can also be used to measure how much of charge has been fed or has been taken out from a battery or a cell. So if we integrate the current, like let us say I have 5 amperes of current, I am pumping it 5 amperes for 1 hour. So I have 5 ampere hour of charge being pumped into the battery. Same for the discharge as well. So we will look at the one of the algorithms. And then there is the use of current for computation of the internal resistance for voltage compensation. So while using balancers and all, so different cell based on the cell capacities, temperatures, the internal resistance of the battery can vary. If we want to compensate for those changes, then we have to use the currents that are flowing through those cells in order to compensate for that. So how do we achieve that? We can use current shunts. So current shunt is basically a series resistor, a precision series resistor which is placed in the current path. So once it is placed in the current path, so what it does is, like let us say I have a battery here. So this is a battery and then I have a load. So I will, if I want to measure the battery current, then I will put a precision series resistor. So this is what we call as a current shunt. So now based on the current, if I know the resistance, so precision resistor means its resistance will vary within a very small tolerance. So I know, if I want to know my current, then what I can do is I can measure the voltage across it, and it will be given by simple relation. So now I know my voltage, this is what I am sensing. Resistance I know because I have used the precision resistor, then I can find out my current. So it is called a current shunt, but it is you placed in series with the current path. That's how the current is being measured using current shunts, and it will give the voltage which is proportional to the current. And then we have direct transducers like Hall effect based sensors, which directly give the voltage, a voltage proportional to the current. So here are the some pictures taken from the data sheets, like this is a RSA 100 current shunt, which is a chassis mount. So you can see that it is 0.001 ohms. So these have to be, and its tolerance, it is 0.25% tolerance and 10 watts. The resistance is very less, but it is 10 watts. That means it can handle larger amounts of currents, even hundreds of amperes of currents. And it is being placed on a heat sink because this resistor is in series. It will carry the load current, so it will get hot. So we have to take out that heat. That's why most of these current shunts need to be placed on heat sinks. So there are chassis mount packages which are available also. Then this is a LEM current transducer. So this is a Hall effect sensor. So these are the terminals. So the current will flow from this side to that side or the other way around, and accordingly here are the signal pins which will generate the voltage proportional to that current. So this is a part number known as LESR NP, 15 NP. So accordingly we have 6, 25, 50 NP, all those current transducers. Now we have looked at the measurements. So coming to management. So how once the BMS, it takes in all the data, like measurements are available, voltage, current, temperature, how it can perform any corrective action or how it can manage the cell or a battery to be in its safe operating area. So first thing is protection. It can protect the battery by allowing the battery or not allowing the battery damage due to operation beyond its safe area. Right? It can stop the charging or the discharging. Then it can do something called as cell balancing or redistribution, which essentially maximizes the cell capacity. How it does, we will look at that. And then thermal management, like once you sense the temperature, you can actively turn on a fan or activate cooling mechanisms so that you can bring the temperature back into the safe area. So these are some indicative ways in which a BMS can essentially protect or manage the battery. There are advanced BMS which can perform more functionalities than that. But these are the basic requirements that has to be fulfilled by a BMS for a battery. So now coming to the cell balancing or the redistribution. So what happens, like so we talked about a battery pack, and let us say we have a battery. So there are several series connected cells. So in series the current stays the same, right? The current that is being fed or taken out from the battery, that stays the same. However, there can be mismatches in the capacity. What are those reasons? There are, like, the battery will have a self-discharge and its manufacturing tolerance, due to which the net current that is being fed into the battery or into each cell is not same. There can be variation in the internal resistance due to, again, manufacturing tolerance, shape. Then there can be auxiliaries connected to the cell. So here we saw that we can connect sensors to each of the cells. So these are auxiliaries, these are performing measurements. So this will draw some amount of current. If there are mismatches in these sensors, which obviously in practical world there will be, so the net current that is being fed into a cell will be different, because it will have its own discharge, own circulation, which will be separate, different for each cell. So now if we have one cell which is charged to, let us say, 80% and one cell which is charged to 50%. So let us say we have two cells connected in series. One is sitting at 80% state of charge, one is sitting at 50% state of charge, and each one of them has its own voltage sensor and monitors, right? So and now we are charging. Let us say we are charging. So while charging, its voltage will reach the maximum value early on it will reach. So let us say once it reaches to 100%, it gives a command that stop the charging. So it has reached 100%, but how much has this reached? It has reached only 70%. So this cell is undercharged, but this will give the command like, you can charge me more. You can push in more current through this cell. So what does so if the algorithm is not fed properly, or if there is unbalances in the battery in the cells, what it can lead to is like this charge this over fully charged cell or the most charged cell in that string will get overcharged. It will get overcharged beyond its capacity. Same goes for the discharge case. So same goes for the discharge case in the sense, if we have like 80% and then 50% and we are discharging it. So we are now taking the current out of the cells. Now this can discharge only 50%. So, but when it comes near to 0, we should not go to 0, but if for example, if it comes near to 0, then this will come to 30%. This has some capacity still left and this has reached its end point. Then this will tell that, okay, I am fine, you can still take out more charge, you can still keep on discharging. That will lead to higher discharge of this cell, which can eventually damage this cell. So if any of the cells in a string gets damaged, the whole battery pack fails. Right? That's why cell balancing is essential. So now we saw that if the case is like this, then we are only, so let us say it gave the command that, okay, the cell is fully charged. Based on this, we are detecting that we have 80% charge. But how much are we able to use? Only 50%, correct? We are able to use only 50%, and once this process happens over time, these capacities will keep on degrading. These capacities will keep on degrading. That is why we need to have cell balancing algorithms which can at least balance out the capacities. Like if it is one at 40%, one at 60%, both can be at 50%. So therefore, we need to balance out the cells so that we can maximize the whole pack's capacity. We can use the pack's capacity. Otherwise, we will be overutilizing one or underutilizing one. We cannot use the full pack capacity. So how it is achieved? Based on voltage or state of charge. So here I was demonstrating a state of charge based equalization or state of charge. So we have 80% charge, we have 30% charge, 50% charge. Based on that, you equalize the cells, or there can be voltage based balancing also. Like you have different voltages of the cells. So those can be balanced out so that we have same voltages across each cell. Which one is better, which one is worse, that needs to be looked at with proper care and with focus to the battery chemistry. Sometimes the voltage can be a indicative of the health, sometimes state of charge can be a indicative of the health. So this overall affects the cell and the battery pack's health. So so how do we balance it? There are passive balancing and active balancing. So what is passive balancing is, we will, if a charge is overcharged, if a cell has more charge than the other, then we will take out that charge and we will dissipate it as heat into some resistor, or let us say BJT, like which is operating in its linear zone. Or what we can do is, we can do some active balancing, which is non-dissipative. Non-dissipating means we will transfer the charge from one cell to the other, or from one cell to the battery, or from multi-cell to multi-cell actively by using any active method such as power electronic converter. So this is what I was discussing, like passive balancing. So we have the sensors, MCU, then it feeds all the data into a balancing algorithm. So based on that, one MOSFET or the other will be turned on. Let us say this first cell is overcharged, so this MOSFET will be turned on and it will dissipate all its extra charge as heat into all these resistors. So once it is balanced, all the MOSFETs will be turned off. So this is passive balancing, but this is lossy, and this cannot be employed for systems. Let us say like we have some battery packs that are being used for satellite power supplies. So there we cannot afford these losses. So therefore we go for active balancing. So in active balancing, what do we have is, we have the MCU, again same thing, but instead of this network, resistive network, we have a power converter. So what are the different topologies, or how it is done, that we will be discussing later. So this is a comparison of the various algorithms or topologies that are being used for cell balancing. So this was compiled by one of the MTech research students in our department who was working with Professor Vinod. So this data, he has done a survey, and based on that he has compiled it into in his thesis. So we have cell to cell equalization, we have cell to stack, adjacent cell equalization, or multi-cell to multi-cell. So how the complexity varies what are the requirements for the voltage sensing, and what is the speed of the equalization. So this all matters when we have to consider all these algorithms. Right. So we will see some examples of these algorithms later. So now we have covered the management part, then coming to the analysis or the evaluations. So what a BMS can evaluate from the data that has been given to him. So it can estimate the state of charge or the depth of discharge, like how much it is charged, what is the current capacity that can be extracted, or what is the depth of discharge, how much has the battery been discharged, how much charge has been taken out. Then it can help in computation of the internal resistance. It can help us to compute the overall capacity, because over the battery life cycle the capacity keeps on degrading. Then this is a metric that we can use to define the health of the battery or the life cycle of the battery. So before we go, some definitions like state of charge, the charge that is releasable divided by the nominal charge. So this is the state of charge that is present in the battery. Then we have the depth of discharge, so how much charge has been released divided by the nominal. Then we have the total charge of that battery, that is the charge that can be released and charge that has been released. If we sum that, we get the total charge. Now this total charge does not stay constant. This fades out due to reactions, due to like physical damages, due to abuse by the user. This overall charge fades out. So if that charge fades out, in order to consider that effect, so that figure of merit, that is state of health, is defined as the Q total by Q nominal. Because while production the Q nominal is set, like it is a 50 ampere hour battery, but over time, let us say after 1 year it has become, total charge has become 40 ampere hour. So the state of health has degraded by 20% in 1 year. So like that. And SOH can be determined by the state of charge and by the sum of the state of charge and depth of discharge. So how this is being used by the BMS, that depends upon the algorithm. But this is essential when we are designing a BMS or when we are using a BMS. We should be aware that these things can be used to perform, or these evaluations can be performed in order to increase the battery life or like best efficiency. We can get the best efficiency out of that battery. So coming to SOC estimation, so we had seen that the state of charge varies non-linearly with the open circuit voltage, right? So and online estimation, like while the battery is connected to a vehicle like a charger, or it is giving the power to a motor, while it is online, while it is functioning, while charging, discharging, the SOC estimation is challenging because there is internal resistance, then there is the change in the open circuit voltage is fixed, but then there will be a IR drop which will give the terminal voltage, and we have only access to the terminal voltages. That varies or that differs from the OCV. So we cannot use directly the terminal voltage to estimate the SOC. Rather, we can use the open circuit voltage. So like we have to measure the open circuit voltage at zero currents, right? So in between charging, we have to stop the current and then measure the open circuit voltage and estimate the SOC. But that is challenge. That is not practical, right? Because while charging, how many times will you stop and estimate the SOC, right? That's why we have different indirect methods like voltage translation or the Coulomb counting, right? So what does voltage translation means is, we can directly look at this voltage and then tell the SOC. Right? If we look at this voltage, if it is at 2.5% or 2.5 volts, then we can say that it is at 0% SOC. If it is 3.65 volts, we can tell that it is at 100% of its SOC. But this is only and for detection of the SOC in between, we need a linear characteristic. So that's why voltage translation can be easily applied to those chemistries where the open circuit voltage varies linearly with the charge as it is charged or discharged. So here, what is the merit? What is the merit of using voltage translation is, it is alone sufficient. If it is linear, it is alone sufficient for SOC estimation. But the limitations, as we discussed, the terminal voltages keep changing as the internal resistance is there, and it also keeps changing with the SOC. The OCB needs to be measured at zero or very small current. So we need to stop charging or discharging, then we have to measure it. So that is the challenge, and it is not applicable across a wide range of chemistries because every chemistry may not have a linear characteristics. Therefore, there is another method like Coulomb counting. So what does Coulomb counting mean is, coulombs is like the unit of charge, so we will count how much charge has been given or taken out from the battery. So that is basically the integration of the current that gives the charge pumped in or out of a battery, and it can be used to compute the remaining charge in the packet, in the battery pack. So let us say we have a example current profile like this. So it is like a constant current charging for some duration, then the current slowly gradually decays to near to 0, then we stop charging. So let us say from t equal to 0 I want to compute like what is my SOC currently at time equal to t. So I have to integrate. So the charge I need to know at time t, which I can integrate like 0 to t I dt plus q naught. So the limitation here is the initial charge q naught, that needs to be known. If we do not know the initial charge, then we will not be able to tell the final SOC. We will know only the charge that has been pumped, like the delta Q that has been taken in or out of the battery, but we will not tell the final SOC based on this Coulomb counting method. So that is the limitation. But and the overall capacity, as we talked about, the Q total that decays or that fades away with reactions, with physical damage, abuse, so that depletes over the time, and this algorithm does not consider those effects, because if the capacity has degraded, so you can, let us say 50 ampere hour to 40 ampere hour charge, the capacity has degraded and you have pumped in 40 ampere hour of charge, then you will predict based on your previous experience that it is 80% SOC, 80% charged, but actually it is fully charged because of the decay of the nominal capacity or the Q total. So that is not taken into consideration while in this algorithm. So we will look at one example of SOC estimation by Coulomb counting only. So how do we digitally implement it? So we have to use like microprocessor, and we have to sense it and we have to implement it. So there are various types of discrete methods we can implement. So this is the example of forward Euler, where we use the, in order to determine the charge at the present interval, we use the current at the previous interval and then we multiply it with the time step. Similarly, backward Euler is like, in order to predict the current at the or the charge at the nth instant or nth time step, we have to use the current at that time step only. So here you can see the error that can come in, like one place we will overestimate, one place we will underestimate, but in order to get a fair approximation, we can use trapezoidal algorithm, where we use both the current as well as the past samples to perform the charge estimation. So this is at the nth instant. If we sum it over, if we perform this computation from t equal to 0 to n, we can get the how much charge has been fed into the battery. Still then it will need the initial SOC or the initial charge. Okay. So I will show the MATLAB script after I finish the presentation. So just discussing some of the BMS topologies. So let us say we have 5 different cells. So we can have a centralized BMS that controls or balances or performs the management of all the cells together. Then we can have modular BMS. Like if a BMS has been built for 2 or 3 cells, then they can be connected in such fashion. So modules, we can put it. Then there can be master-slave modules. So this will be called as a battery monitoring unit. This will be called as a battery management unit. So it will just monitor and feed the data, and it will perform some calculations and then feed back the control signals. Like that. There can be also individual cell BMS also, but that will again become costly. Like each cell will have its own BMS. So that can become costly depending upon your application. So what are some of the examples of commercially available BMS? So these are like, so these are the part numbers, like this is from Atmel, this is from eLithium, then we have some ICs from Texas Instruments. So you can see here the maximum cells that it can cater to is 4. And this can cater to 255 cells at a stretch. Then the balancing algorithm inside the chip has been fed, like this only takes care of, this can only accommodate passive balancing by using dissipative resistive divider, and it is external, it is not internal to the IC. Similarly, these offer external balancing but passive and active both. However, the Texas Instruments, it is internal and it is passive. So temperature monitoring, it can monitor the temperature of each cell, it can monitor the temperature of the whole pack. Then there is communication, so it has to communicate with the system, like the external system, charger or a motor or a motor control unit, vehicle control unit. So these are the different types of communications that are being used in this state-of-the-art commercial BMS. So these are like, this is the E-lithium EL02 based BMS, and this is a single cell based evaluation kit by Texas Instruments. And then this is a NXP reference design bundle, which we can like for academic purposes we can get these bundles, which include battery monitoring unit, cell monitoring unit, as well as junction boxes. So here we can take care of like multiple functions at a time with these evaluation kits. Then some examples of like active balancers. So here I am showing the example. So this has been taken from literature. So these are like adjacent cell to adjacent cell balancer. So this is like a switched capacitor topology. So according to the switching function, two adjacent cells will get balanced at a time. So then we have like cell to stack equalizer. So there are, let us say, 10 cells in a string or a battery. Then we will have a single converter which converts all, or it is kind of like a boost converter. We will put it and all the cell voltages will be converted into a common DC link. So this uses a common DC link to equalize the voltages. So and here are like, it is modular kind of structure. So here you can have one balancer, like n number of balancers for these cells. Then there is cell to cell balancer. So this is again taken from reference. Professor Vinod's student, he has worked on it. So this is like cell to cell balancer. So this is a like a cell selection network. So it based on some detection algorithm, the overcharged, undercharged cells will be identified, and the charge from that cell to a particular cell will be transferred by selecting which cell we want to equalize. So this is like a cell to cell balancer. So any cell to any cell. But these algorithms like cell to cell balancer or cell to stack balancer can be very slow. So therefore there is like multi-cell to multi-cell balancer. So this is the work by Manish, who was an MTech research student here working with Professor Vinod. So this is the topology, like the multi-active half bridge topology that transfers or that balances out multiple cells at a time. So here we can achieve the balancing at a very fast rate. So yeah, so now I will show one algorithm like the example of Coulomb counting, so that I prepared.
And also I had one more question on the internal cell resistance and cells going degrading at a different rate, right? In that example, does DC fast charging, repeated DC fast charging can also throw cells out of balance? Because that has been heard as one of the key causes of, I mean, recent vehicles, at least Tata explicitly claims that is the way. That if you repeatedly DC fast charge, that means high rates of current are pumped into the battery pack, and the internal balancer doesn't get enough time to balance out the cells, and you drive away.
Correct.
So and then you stay at 80%, or you don't give it enough time, and then it can throw cells out of balance.
Correct.
Is that also a possibility?
Yes, yes, that is definitely a possibility. Because as you mentioned, like if you pump in, if you try to fast charge, like if a cell nominal, we can charge it in 5 hours. If you want to charge it at, let us say, 1 hour, fast charging we want, then definitely we have to pump in more current, and that does not give enough time for the other algorithm. Then we may have to put an advanced BMS. Let us say we have to put an advanced BMS with all like every of the measurements going on simultaneously, so that the bandwidth, and like we have to employ a high grade processor for that also, which has that much of bandwidth and computational capability to compute and perform the measurements, perform the measurements and feed the algorithm, like the battery balancing algorithm, to the balancer circuit. So definitely, yeah.
Does it actually shut down the balancing when the system is running, or it will continue balancing?
That I am not aware of. I may need to look at the exact like the structure or the algorithm that they are following. So I may not be able to comment about that right now.
Sure.
So,
and just to add to his point, again he showed different examples, right? The way you can sense either parallelly if you put multiple sensors, or you do it serially. If you do it serially, or if you use selector networks, that will slow down the algorithm. So it's cost versus speed trade-off. Then likewise, even the balancing algorithms, he showed a table where he was comparing the speed of different algorithms. So if you're using an active balancer with a multi-cell to multi-cell, you can immediately take out charge from any cell and feed it to any other cell. But sometimes you will only take the most overcharged cell and the most undercharged cell if you want to limit the cost of the electronics. But then, you do it again sequentially. You first take the overcharged cell, then you take out some charge, and then you go to the next. So if you use those kind of slow algorithms, then if you are performing fast charging, you may not have enough time to balance out. It'll quickly start diverging. Finally, these algorithms will also have some time for it to, let's say, stabilize or come to a balance. So we have to look at the trade-offs. It depends on the application, it depends on the charging or discharging rates, and it's mainly a cost trade-off.
And is there a consideration that some of the charges bypass the BMS during especially DC fast charging? So that could also be a concern.
Again, it depends on the implementation. For example, some of the BMSs, they may not be actively involved in protection. They may only send a command to the controller saying that, okay. So if that is the case, there's a possibility that it can be, there can be an override. But again, the thing is, there are different variations, and many a times, that is why automakers are trying to develop these themselves, because they want complete control. But if you're buying something off the shelf and if you're integrating, then you're limited by the hardware. But all these options are out there. There are BMSs, it depends on the priority, so you can prioritize. If you say that the BMS takes the first priority, then if BMS tells don't charge, then you will not charge. But all these are possible.
Sure, thank you.
I'm sorry if you find it very basic question. Like, since there is a one-to-one mapping between the cell and the sensor, so I wonder, like, is it an obligation from the battery manufacturer to fit that sensor onto the battery, or since I assume that it's part of the BMS system, so there should be is there any standard communication protocol that is followed to fit those sensors, or as part of interface those sensors to the battery or the cells?
If you directly buy a battery or a battery pack which has only 2 terminals, then however complicated BMS we can develop, we cannot use it, because even if we have hundreds of sensors or channels, we will not be able to use that. So it is, in my opinion, it is the task of, like, while manufacturing itself, we can give the provision to fit on or clamp on a BMS. Let us say I have a BMS board which has 10 different sensors and there are 10 cells or 8 cells. Then I can clamp on that to the battery. So that provision has to be given by the battery manufacturer as of now. That is what I feel, because if we have only 2 terminals, we will not be able to use.
So what is the present state of that? Is it like they kind of, you dictate these terms, like the companies dictate these terms to
manufacturers? Maybe I can take that question. So what many of these automakers do is they buy cells and they make their own stack or battery bank. Right. So they have complete control and they can put their own BMS or whatever. So they just buy cells and they make their own stack. So if you are not just buying a battery as such.
So out of the 3 pack, like cell, pack, the sensors must be fitted somewhere in the pouch then, right? Block level, right?
Yeah.
Because that's where individual cells are getting...
Correct. Yeah. If you look at companies like Tesla, they'll buy all these small cells, individual cells, and they'll make a pack out of it. And they'll put it appropriately in the car because they'll have some space constraints and where they can put the battery. So it is dependent on the manufacturer.
Okay. So a subsequent question to this is, say, assume that there's a very stringent grading that happens between the cells, and you pack only those cells which are like almost same.
Correct.
Right?
Correct.
So would it make sense to, like, have only one sensor per block or per pack?
Yeah, it's again a question of cost, right? It is good to put individual sensors, but it may not be practical from a cost perspective. So initially, you do a lot of testing and you identify cells which are very closely matched so that the differences, when you're selecting, is not that high. Then you cut down on the sensors, assuming that hopefully the degradation will be similar. But again, there is a possibility of danger.
I see. And I have a last question. Third question is with respect to analysis.
Yeah.
Now, most of these BMSs seem to be, catering to, or, doing analysis on a standalone basis. Is that like on a per battery pack basis, right? Is there any learning or experiment done to understand behavior of similar kind of pack, and the learning obtained from that to be applied on similar kind of packs which are deployed somewhere else?
Because if you look at most of the automakers, they continuously collect all the data from their vehicles. I mean, the BMS is, I think, storing the data in the cloud or something, and they have access to all this data, and they use that to continuously improve.
So any knowledge about whether it really works, the pack to pack level behavior is same, so
that I am also not sure.
Okay.
I mean, because that is very sensitive information, and we will not have access to that.
No one shares. Yeah, I see.
So yeah, how effective it is, I cannot comment.
Okay, thank you.
Quickly go through the algorithm once. So this is a Coulomb counting based algorithm. So for that we need to know the nominal capacity of the battery in ampere hours, and as I mentioned, we need to know the initial state of charge, like what charge is already there in the battery. So once the initial state of charge is fixed, so now I will show the example with two different current profiles. So let us say I have the current one, then so here in the current one I have a 3-hour charging profile. So coming to the algorithm here, as I showed different algorithms like forward Euler, backward Euler to implement in discrete domain. So this is the example of forward Euler algorithm where I am predicting, let us say I am predicting the t plus 1th instant current or the charge by using the previous values. So here I am using all previous values like t and t here, previous charge and previous sampled current. Then I am multiplying it by the sampling time, which is, for my case here it is 1 minute, and then in order to convert it to ampere hour I am considering divided by 60. Then I am calculating the final SOC, that is the final state of charge, by dividing that charge by the capacity. So if I run this, then so this is just a UI for demonstration that I had prepared. So once it is charged, you can see that it will show that it has been charged to 99.58%, and this was the current profile. So I was continuously feeding in 20 amperes of current for 3 hours, that is 180 minutes. Initial state of charge was 25%. So if and capacity is 80 ampere hour. So there is 60 ampere hour of capacity left. So 20 into 3 hours, so 60 ampere hour I am feeding. So my charge, final charge is close to 100%. Now let me change the current profile. So the algorithm stays the same, but my current profile is now changed. So let's see. So here again from 25% it will start charging, but that after that at the end it will become slower, and it will charge until 97.8% only, because I have a different current profile. So this is a 4-hour current profile that I am feeding. So for 150 minutes, that is 2.5 hours, I am just feeding in constant current. So that has charged it to some capacity, and then my current is reducing. If my current had stayed at 20 amperes, then within 3 hours I could have charged to 100%. But my current now has reduced, because let us say of CCCV algorithm that it demands the voltage to be maintained. So the current needs to reduce. So once the current reduces, the charging speed also reduces, and it charges up to 97%. So this was just a example of the Coulomb counting mechanism. Advanced mechanisms are there in literature which can be implemented. So this was just an example using a forward Euler method. So yeah, so that is what I had to present today. Thank you.